Welcome to my video about gravity and anti-gravity. In part 1, we begin by reviewing current theories and revealing a number of massive mistakes. We then use 3D animations to explain how the pull of the Earth's gravity is created from the flow of time. In the second part, we use animations to show how large collections of atoms create the Earth's gravity. And then we extend these ideas to explain anti-gravity effects in superconductors. Finally, we look at steps to invent anti-gravity. A very popular idea is that we use something called a quantum field theory to explain gravity. Unfortunately, this approach just doesn't work with Einstein's gravity equation. Quantum states jump in steps, but Einstein's equation needs smooth, continuous variables. Theorists have really struggled to find a solution to this problem. Number 1 is string theory. It attempts to explain everything in the universe as tiny vibrating strings, much smaller than even the tiniest subatomic particles. It requires something called supersymmetry, which predicts partners for all the known particles. To date, none have actually been found. Supersymmetry requires 10 dimensions. With so many dimensions, the landscape gets confusing. There are just too many solutions and the theory just can't be tested. It gets worse. The theory makes a serious error predicting the value of Einstein's cosmological constant, the energy density of a vacuum in his theory of general relativity. The value should be positive, yet string theory gives a negative value. Something has gone seriously wrong here. Another popular approach is loop quantum gravity. It proposes gravity is made up out of ridiculously small loops of the order of the Planck length at 1.6 times 10 to the minus 35 meters, the smallest resolvable length. Another problem. The mathematics is really struggling to reproduce the effects of general relativity and classical gravity at large scales, and there is serious doubt that this is actually possible. The theory predicts that light at shorter wavelengths will travel slightly slower. However, experiments have failed to detect any change in the speed of light. These problems suggest that quantum field theories are wrong. It is only particles that are quantized, not the fields that they're created out of. There are 2 published theories for non-quantized gravity. Jonathan Oppenheimer's theory is far the most advanced. It proposes that only the right-hand side of Einstein's equation is quantized. This makes incredible sense given the huge number of atoms needed to create a gravitational field. Einstein's equation is 100 years old, and it badly needs a facelift. Its analytical approach requires solving complex and incredibly difficult differential equations. We only too easily forget it was invented a long time before computers, and it fails to harness the power of iterative algorithms. A popular massive mistake is not realizing that the equation is recursive. Changing the energy tensor changes the curvature of space-time, which moves the distribution of energy again. We need an iterative approach to harness its power, which is very easy with modern computers. Another problem is modeling more contemporary forms of energy, such as electromagnetism and light particles. The equation really struggles predicting the gravitational lensing of light because of the speed of light being constant. It will need modifying to show how large collections of atoms produce gravity. We urgently need to debunk the exact meaning of quantum with subatomic particles. Definitions on the internet fail to reveal the true reason for the quantized behavior. We forget that quantized systems exchange energy perpetually between one or more forms. The massive mistake is not realizing that it is the particles making up the field that are quantized, not the field itself. Compare energy stored in a spring with energy in a swinging pendulum. The second massive mistake was not realizing that the particle wave function can give rise to a static field. Again, we have our number 1 enemy, the black box, and it has disguised gravity fields at the heart of atoms by another name, and we fail to see the connection with large-scale gravity. The 3 diagrams taken from my previous video show simple examples. As a general rule in physics, dimensions are used to tag particles with associated fields. The charge or mass associated with a particle is due to the amplitude of a displacement in a unique dimension. Gravity does not differentiate between particles of differing electric charge, and we deduce that it is a superset of normal spacetime. Electric charge must be a subset because particles exist without charge. When we add the fifth dimension, the pieces of the gravity jigsaw puzzle suddenly fall into place. The work or energy needed to stretch and project spacetime explains why energy equals mc squared. Gravitational lensing effects seen in astronomy require that the path length of light to increase when it passes through a region with a strong gravitational field. The distances are being stretched by a projection of normal spacetime into an extra dimension. When matter disappears into black holes, it needs to go somewhere in order to conserve energy. Also, there is the expansion of our universe to consider. Displacement in a fifth dimension would explain all these effects. There are two popular theories in physics which use a fifth dimension. The first was Kaluza-Klein's theory in 1921. The fifth dimension here was of microscopic size and therefore more suited to electric charge. Later, in 1999, Randall and Sundram developed their theory originally to solve the hierarchy problem, to explain the huge difference between the measured and predicted values of physical constants. However, their RS2 model, with a single system of dimensions, turns out to be very convenient to explain gravity. Newton's equations are simple to use, but beware their limitations. The popular left-hand equation tends to infinity as the radius r tends to 0. It only gives the correct answer for values of r larger than the radius of the planet. For a radius inside the planet, the right-hand side equation must be used instead. Newton's equation is only valid for static gravitational fields. This is frequently overlooked and has led to massive mistakes in cosmology theory. With dark theory explaining the rotation of galaxies, Newton's equation gives a value too low, because the background expansion of the universe is not taken into account. This was reported in 2022 in a paper titled Gravitational Orbits in the Expanding Universe Revisited. With dark theory regarding the rate of expansion of the universe, recursive background conditions are being overlooked. In 2007, these ideas led to a new theory called timescape. It showed that in cosmic voids, time would flow up to 38% faster, speeding up the rate of cosmic expansion. Einstein's gravity equation must be used to correctly model these problems. We now move on to part 2 of this video, where we use 3D animations to show how gravitational fields work. We begin by plotting the Earth's pull or acceleration according to Newton's equations. The coordinate system shows acceleration on one axis and two spatial dimensions on the other axes. Note that the force acceleration drops to 0 at the Earth's centre, and the slope changes from linear to square law as one moves outside the Earth. To get the familiar bell-shaped curve, we need to plot gravitational potential energy as a function of radius. Potential energy is often taught at school as m times g times h, but this is only valid for height small compared with the size of the Earth. Because g varies with height above the Earth's centre, we must integrate the acceleration equations. The linear slope now turns into a square law, and the square law outside the Earth turns into a cube law. Time slows down the deeper one goes down the gravitational well. This is because of the time delay needed for a beam of light to cover the extra distance projecting into the fifth dimension. This effect is not observable inside 4D spacetime, so nature slows down time instead. If only time slowed down, then distance measured by timing beams of light would appear too long. So according to the theory of special relativity, space must contract in direct proportion. This is what's shown in the animation. The Earth is now not shown, but the blue circle marks its correct position. We now show how curving spacetime causes acceleration from the flow of time. We need to animate the flow of time, so we now use a different coordinate system, with time plotted against a single spatial dimension. The third axis is used for the projection of spacetime into the fifth dimension. In this animation, we build up the gravity field step by step. First, we project spacetime in order to create the gravity well. You might have noticed a problem. The distance markers on the red light beam are stretched apart. This is not possible because the speed of light is constant. We must adjust the position of the light path so that distance and time are shown correctly. Notice how the light beam is now shown crooked because of the extra time it takes to cross the gravity well. We now need to apply time dilation to realize this effect. Extra distance in the fifth dimension is not directly observable. Notice how the light beam now appears blue shifted as seen by an observer placed at the bottom of the gravity well. We now notice another problem. Distances at the bottom of the gravity well appear too long when measured timing a beam of light. Special relativity corrects this error by shrinking space in direct proportion to time. Notice how the rectangles at the bottom of the well have changed back into squares. They now appear the same as the grid outside the gravity well. Also, the beam of light exiting the well is redshifted as seen by a viewer outside. In a real gravity field, all these steps happen together. The Earth is shown as a cylinder because there is only one spatial dimension visible. We can now show how gravity causes acceleration. We do this by animating the flow of time. The red line shows a single point in time, and the yellow ball shows the free fall trajectory under the acceleration of gravity. Notice how the ball's acceleration increases as it gets into the region where space-time is curved the most. Here is the same animation viewed from a different angle, showing the gravity well far more clearly. Watch out for part 2 of this video, where we go on to learn some cutting-edge stuff, such as how to create anti-gravity fields. Thanks very much for watching.